Hello, and welcome to Linear Algebra. This is lecture 38 on the Jordan canonical form. Last time, we talked about the characteristic polynomial. Of a matrix. This time, we want to use some of the things we discussed last time, such as the algebraic multiplicity of eigenvalues, to talk about what can you do for matrices that are not diagonalizable. Okay, so today we're going to restrict the field to be the complex numbers, so I don't have to keep talking about algebraically closed fields and so on. Let's just go ahead and say that we're working with the complex numbers. Also today, I'm going to switch the notation a little bit. I'll say that a vector space V is the direct sum of U and W. Here, I'm going to be using what's called the topological direct sum. Right, so I'm not going to assume that they're orthogonal. So this will mean that if every vector in V can be written as a sum, with U and U, W and W, and if U and W intersect only in the zero vector. Okay, so that's known as the topological direct sum, and that's what I'll be using today. All right, so matrices that are not diagonalizable. So I want to revisit when a matrix is diagonalizable in terms now of the algebraic multiplicity. I want to use that to somehow figure out if a matrix is diagonalizable, and if not, then what fails and what can you do? What's the next best thing? So let's start by saying that since the complex numbers is an algebraically closed field, we know that every n by n matrix is similar to an upper triangular matrix. Right? In fact, we've improved our first version of this using using the QR decomposition. We got what's called the sure decomposition, which says that not only is it similar, but it's similar using an orthonormal basis. On the other hand, we know that A is diagonalizable if and only if there is a basis consisting of eigenvectors. Okay, so let's look at this in view of the sure decomposition, for example. So we may as well assume that A is upper triangular. So let's say that we have A, and we have lambda 1, lambda 2, and so on. On the diagonal, you have zeros below, and then I'm just going to put asterisks above because they're non-zero, but I don't know what they are. I might denote this with fewer symbols by just putting a big 0 here and a big asterisk here to indicate that everything below the diagonal is 0, everything above the diagonal is unspecified. Could be 0, could not be 0. So we know that the elements on the diagonal are the eigenvalues. And they are repeated with algebraic multiplicity. All right, so let's use notation m sub a of lambda to be the algebraic multiplicity of lambda as an eigenvalue of a. Right, so if we list lambda 1 through lambda k, the distinct eigenvalues of a, then we know that if I sum the algebraic multiplicities, I need to get n, right? Because I have an n by n matrix, and the algebraic multiplicities are just how many times each lambda occurs on the diagonal. So for example, if I have a matrix with entries 3, 0, 7, 3, then 3 is the only eigenvalue. Of a, and it has algebraic multiplicity 2. On the other hand, its eigenspace is Eig3a, right? This is the kernel of a minus 3 times the identity, right? Which in this case would be the kernel of 0, 7, 0, 0. And it's very easy to compute that that's equal to just the span of E1, right? So this has dimension 1, right? The dimension of the eigenspace is sometimes known as the geometric multiplicity. So you can see the problem here. This matrix is not diagonalizable. It does not have a basis consisting of eigenvectors. It's because there's only a one-dimensional space of eigenvectors. So the problem is that the geometric multiplicity does not match the algebraic multiplicity. Right? Now we always have that the dimension of the kernel of a minus lambda times the identity is bounded above by the algebraic multiplicity of lambda. Right, so indeed, as both sides of this inequality are invariant, we may assume that A is upper triangular and so because it's upper triangular, it's easy to see that the rank of A minus lambda times the identity is at least the number of non-zero diagonal entries. So the null space of A minus lambda times the identity is at most n minus the number of non-zero diagonal entries, which is equal to the number of zeros on the diagonal. And as we've already discussed, that is equal to the algebraic multiplicity of lambda. Okay, so that in fact is the only thing that can go wrong. A matrix is diagonalizable when you're working over the complex numbers, if and only if the dimension of the kernel of A minus lambda times the identity is equal to the algebraic multiplicity of lambda for all eigenvalues lambda of A. Okay, so diagonalizability is the same as having the algebraic multiplicity match the geometric multiplicity. Okay, so let's prove this. We've basically already done this, but let's write it out. A is diagonalizable if and only if there is a basis of Cn consisting of eigenvectors which is the same as saying that the dimension of the kernel of A minus lambda 1 times the identity plus up to the dimension of the kernel of A minus lambda n times k times the identity. So again, I'm using lambda 1 through lambda k as the distinct eigenvalues of A. That this is equal to n, which is equal to the sum of the algebraic multiplicities. Okay, but if I have k terms here and k terms here, and each one of these is at most as large as the corresponding one over here, but the sum of these and these is the same as these, and these are non-negative numbers, the only way that can happen is if each one of these is equal to the corresponding one of those. Okay. Okay. So now, if A is upper triangular and not diagonalizable, we know what the problem is. The problem is that there's an eigenvalue, lambda, that occurs on the diagonal more times than there are linearly independent eigenvectors. Okay, so for example, let's say that you had a matrix, and on the diagonal you had 2, 2, 2, 7, 7, right? And you have, I don't know what, zeros below, and I don't know what above, right? So, okay, so if you do A minus 2 times the identity, then you would have zeros here, 5 here, 0 below, and who knows above. Okay, so this tells us that the nullity of A minus 2 times the identity is somewhere between 1 and 3, right? So we know you have to have an eigenvector for the eigenvalue 2, so you have the nullity is at least 1, right? And here you can see that E1 is going to be an eigenvector. But the nullity is at most 3, because this has rank at least 2, and so nullity at most 3. Now, if you were to do a minus 2 times the identity and square that, what happens? Well, notice that if we were to think of this in blocks, then this block is all zeros, this block, who knows? And this block is strictly upper triangular. So when I square this, it's going to get further from the diagonal, right? So this block, I'm going to have 0, 0, 0, 0, 0, 0. So who knows? 0, 0. Then here I'm going to have zeros. I'll make that bigger, who knows? I have nothing to say about this block. And then here, those 5s, well, those 5s are going to get squared. So I get 25s, and then 0 and who knows. Okay, so now the nullity of this is at least 2, and again, at most 3. And if I do this one more time, say I do a minus 2 times the identity cubed, then this block is now going to become all zeros, right? So I'm going to have 0, 0, who knows? This is going to become 125, 0, 125, and who knows, who knows, who knows, who knows. And now the nullity of this matrix, this one I do know now, it is equal to 3, right? Because I have these first 3 columns all equal to 0. Okay, so this is something we could do for any eigenvalue. Right, so we know that the kernel of a minus lambda times the identity is going to have non-zero vectors, right? Because this is an eigenvalue, there have to be eigenvectors. So this is not just a 0 vector. Now it's contained in the kernel of a minus lambda times the identity squared, which is contained in the kernel as you take larger and larger powers, right? And this sequence of vector spaces, it's increasing. Because we're working in CN, so a finite dimensional vector space, this sequence has to eventually stabilize, right? These spaces can't keep growing. They have dimension at most n. And once they stabilize, so if you find a J so that the kernel of a minus lambda I to the J is equal to kernel of a minus lambda times I to the J plus 1, then the kernel of a minus lambda times ij is equal to the kernel of a minus lambda I to the J plus L for all L in the natural numbers. So this might be strict, as we saw the kernel of, so over here, right, I don't know what these x's are, but it's entirely possible that this matrix has nullity equal to 1, and then this matrix has nullity equal to 2, and this matrix has nullity equal to 3. We can easily come up with examples like that. So this one would be strictly smaller than this one, which would be strictly smaller than the next one, and so on. But as soon as you get 2 in this sequence that have the same dimension, then the sequence is just constant from there on. That's easy to check. I'll let you check that. I'll just emphasize that this chain of spaces has to stop at some point. In fact, because I have n by n matrices, the kernel of a minus lambda times the identity raised to the nth power is equal to that raised to the n plus L for every L in the natural numbers. So this might not be the first time the sequence stops, but it has definitely stabilized by the time you get to the nth power. This kernel is equal to the kernel of any larger power. Okay, if lambda is an eigenvalue of A, the generalized eigenspace of lambda which I'll denote G eig lambda of A is equal to the kernel of A minus lambda times the identity raised to the nth power, right? So it is the stable space in this sequence. Non-zero elements of the generalized eigenspace are referred to as generalized eigenvectors of A associated with lambda or corresponding to lambda. Okay, so here are the main properties of generalized eigenspaces, generalized eigenvectors. Suppose you have an n by n matrix with complex coefficients and that the distinct eigenvalues are lambda 1 through lambda k. So, first of all, multiplication by A preserves the generalized eigenspaces. Secondly, if I is different from J, then the only intersection of the lambda ith generalized eigenspace and the lambda jth generalized eigenspace is the zero vector. Right? We can generalize that if you have some set of vectors, and these are generalized eigenvectors corresponding to distinct eigenvalues. Then this set is linearly independent. Okay, so just like we saw before that eigenvectors corresponding to distinct eigenvalues form linearly independent sets, so too generalized eigenvectors corresponding to distinct eigenvalues. Right? You can write Cn as the topological direct sum of the generalized eigenspaces. Okay, so here we're making no claim of orthogonality, just that every vector in Cn can be written as a sum of vectors, one from each of these generalized eigenspaces, and there is no intersection between these different spaces. And then finally, for all lambda j, the dimension of the generalized eigenspace is precisely the algebraic multiplicity. Okay, so you can see that this generalized eigenspace looks like it's going to fix the problem, right? The problem with a matrix not being diagonalizable was that the dimension of the eigenspace was smaller, strictly smaller than the algebraic multiplicity. Okay, so the eigenspaces were too small. We've made them bigger by passing to the generalized eigenspaces, and this says that now it's big enough, right? So we can hope to fix the diagonalizability problem because we've added enough vectors. Okay, so let's prove this there. So part one, given, so what we're claiming is that if you give me a vector in the generalized eigenspace corresponding to some lambda, we want to show that A sends that vector to another generalized eigenvector, or possibly 0. But it sends it to another element of this generalized eigenspace. Okay, so why is that true? Well, we know the generalized eigenspace is the kernel of A minus lambda times the identity to the n. So we know that A minus lambda times the identity raised to the nth power applied to V is equal to 0, right? And that's what we want to show is true for A times V. And we want to show that A minus lambda times the identity raised to the nth power of A times V is equal to 0, right? However, if you have A minus lambda times the identity raised to the nth power, and you're applying that to A times V, you could write that as A minus lambda times the identity raised to the nth power applied to A minus lambda times the identity plus lambda times the identity applied to V. Right? So just add and subtract lambda times the identity. Now we get A minus lambda times the identity raised to the n plus 1th power applied to V plus A minus lambda times the identity to the nth power applied to lambda times V. Right? Now, this guy is 0 because V is in the null space of A minus lambda times the identity. And for the same reason, this is 0 because I can take this lambda and pull it out. So both of those are 0, and altogether, this is equal to 0. So that proves 1. For 2, right, so 2 says that if I is different from j, then the only intersection of the generalized eigenspaces corresponding to lambda I and lambda j is the 0 vector, right? So assume B is a vector in the generalized eigenspace of lambda 1 and the generalized, well, lambda I, we're saying, and the generalized eigenspace corresponding to lambda j. We want to show that V is equal to 0. Okay, well, we know that there are, let's say, Li and Lj in the natural numbers such that A minus lambda I times the identity raised to the Li applied to V is equal to 0, but A minus lambda I times the identity raised to the Li minus 1 of V is not equal to 0, right? So we know that some power of A minus lambda I times the identity kills V, right? Well, there has to be a first power that does that. And similarly, for lambda j, there's an Lj, so that this power is 0, but no smaller power applied to V is equal to 0. Okay, so let's proceed by induction on Lj. Okay, so if Lj is equal to 1, so A minus lambda j times the identity applied to V is equal to 0, then A times V is equal to lambda j times V. And if you do A minus lambda I times the identity raised to the Li and apply that to V, then, well, A applied to V is lambda j times V. So this is the same as lambda j minus lambda I raised to the Li applied to V. And we know that this is equal to 0. Now, since lambda j minus lambda I is not equal to 0, this implies V has to be 0. Okay, so that takes care of the case Lj equal to 1. For the general case, let's let W be A minus lambda j times the identity raised to the Lj minus 1 applied to V, right? So by assumption, this is not equal to 0. However, since A minus lambda j times the identity applied to W is equal to 0, because this would be A minus lambda j times the identity to the Lj applied to V, and A minus lambda I times the identity raised to the Li applied to W is equal to 0, we've reduced to the previous case. And we can conclude that W is equal to 0, right, by the case Lj equal to 1. But that's a contradiction, because we had said that W was not equal to 0. All right, so that finishes the proof of property 2, part 2 of the theorem. Part 3 of the theorem says that if you have generalized eigenvectors corresponding to distinct eigenvalues, then you get a linearly independent set. Okay, so suppose we have Vj coming from the generalized eigenspace, right, mu j. Right, so here, let me start over. Let's say, let V1 through V capital N be generalized eigenvectors with Vj in the generalized eigenspace corresponding to mu j of A. We want to show that this set is linearly independent. Okay? So we've already done the case n equal to 2. It's part 2, because if you have 2 vectors and it's linearly dependent, one would be a multiple of the other, right? And so that would mean that each of them was in the intersection of the 2 spaces. But we've just shown that the intersection of the 2 generalized eigenspaces corresponding to distinct eigenvalues is 0, right? So we're done with the case n equal to 2. So let's do this by induction. Assume inductively that this is known for sets of size n minus 1, and that we have a1 b1 plus up to an vn equal to 0, right? So we take a linear combination, we want to show the coefficients are equal to 0. Applying a minus mu n times the identity raised to the lowercase n to both sides, we get a1 times a minus mu n times the identity raised to the n applied to v1 plus dot 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 plus a n minus 1 a minus mu n identity raised to the n applied to v n minus 1 equal to 0. I don't have to put a term for the vn because this kills vn, right? Vn is, sorry. Vn is in the eigenspace, generalized eigenspace corresponding to mu n, and so applying a minus mu n times the identity raised to the n to Vn kills it. So great, so now we have n minus 1 terms, and each of these is still in its corresponding generalized eigenspace. So by inductive hypothesis, but we know that each of these is still in the same generalized eigenspace by property 1. So we can apply our inductive hypothesis, and we get that a1 is equal to 0 all the way to a n minus 1. Then plugging these coefficients into our identity a1 v1 plus up to a n vn equal to 0, we see that an is also equal to 0, right? Like we wanted to show. Okay, so next, property 4. Property 4 says that we can write Cn as, so we want to show that Cn is equal to the topological direct sum of the generalized eigenspaces right? So what does this mean? We're claiming that every vector in Cn can be written as a sum of generalized eigenvectors, and that it can be written in that way in only one way, right? So the only one way is clear because of 3. We've shown that they're generalized eigenvectors corresponding to distinct eigenvalues give you linearly independent sets. So what we need to show is that that every vector in Cn can be written as a sum of generalized eigenvectors. Okay, so not surprisingly, we'll do this by induction on n. If n is equal to 1, then every non-zero vector is an eigenvector of A, so we're all set. If inductively we know this for complex vector spaces of dimensions less than n, then given A, we know it has an eigenvalue and we can write Cn as the topological direct sum of the generalized eigenspace and the range of A minus lambda times the identity raised to the nth power. So I'll let you prove this equality. Right, remember that A minus lambda times the identity raised to the nth power is it has null space equal to this generalized eigenspace, and that this is where it's stabilized. So also the null space of this matrix is the union of the null spaces of the powers of these matrices, and correspondingly the range of this matrix is equal to the intersection of the ranges of the powers of this matrix. So I'll let you prove this. This is very similar to something we proved in the lecture on triangularization. But just in the interest of time, I'm just going to accept this. Now, the range of A minus lambda times the identity raised to the nth power is preserved by multiplication by A. That's easy to see. And has dimension less than n, right? Because we know that there is at least one eigenvector corresponding to this eigenvalue, so this generalized eigenspace has dimension at least 1. So we can apply our inductive hypothesis. Right, so that takes care of 4. Finally, 4 gives us 5. So remember that 5 says that the dimension of the generalized eigenspace corresponding to lambda j is equal to the algebraic multiplicity of lambda j. So since Cn is equal to, well, in fact, let me just say from 4, we know that the dimension of the generalized eigenspaces add up to n, which is what the algebraic multiplicities add up to. But since we have an inequality, the dimension of the generalized eigenspace is at most the algebraic multiplicity, right? Again, just by thinking about the upper triangular case. Since they sum to the same n, they must actually be equal. Okay, and that finishes the proof of the theorem. Okay, wonderful. So already that's enough to improve our diagonalizability results. Because what you could do given a matrix, size n by n with complex entries, since the complex numbers can be written as the topological direct sum of the generalized eigenspaces, there is a basis of Cn consisting of generalized eigenvectors. Right? So just take a basis for each generalized eigenspace, take the union, and that will give you a basis for Cn. Okay? If you write A in this basis, so take the linear map given by multiplication by A, and then find the matrix associated to that linear map with this basis, you'll find that A is similar to a block diagonal matrix. Right? So something of the form so you'd have A1, A2, and so on up through AK, and zeros everywhere else. So it looks like a diagonal matrix, except that these capital A's are not elements of the field, they are matrices. So each AJ would be a matrix, square matrix of size given by the algebraic multiplicity of lambda j with complex entries. Okay, now each one of those, well, it's just the matrix corresponding to A restricted to the generalized eigenspace. So, well, using theorems we've already developed, every matrix with complex entries is similar to an upper triangular matrix. So we can certainly arrange for each of these AJs to be upper triangular, right? So let me write that. We can choose bases so that each AJ is upper triangular. So for example, if we have a matrix like we were looking at before, where we have 2, 2, 2, 0, 0, and then zeros below, and who knows, above the diagonal, then this, we've improved it. Now we know that it's similar to a matrix of the form where you have 2, 2, 2, something, something, something. And then here, 7, 7, 0, something. And then here, zeros. Okay, so we've improved our model form for a given matrix. Instead of being upper triangular, now it's block diagonal, and each block on the diagonal is upper triangular. We can do better. We can improve further and get a block diagonal matrix whose diagonal blocks are what are called Jordan blocks. Okay, so let me tell you what a Jordan block is. First by example, so J lambda 2 would be a matrix like this. 2 lambdas on the diagonal and then a 1 above the diagonal. J lambda 3 would be a 3 by 3 matrix with lambdas on the diagonal and then 1s on the sort of diagonal immediately above the principal diagonal. J lambda 4, you would have a 4 by 4 matrix, lambdas on the diagonal, zeros below, 1s immediately above, and then zeros. In general, J lambda m is an m by m matrix with complex coefficients. Is equal to lambda times the identity of size m by m plus what I'm going to call nm, where nm has ijth entry, 1 if j is equal to I plus 1, and 0 otherwise. Right. So it's just ones on the sort of diagonal immediately above the actual diagonal, and zeros everywhere else. Right, so this looks like lambdas on the diagonal, ones immediately above that, and zeros everywhere else. Notice that the matrix n sub m, it's easy to see that n, m, and m squared, and up to n, m, m minus 1 are not 0, but n, m raised to the mth power is 0. It's the 0 matrix size m by m. Okay. So, for example, let's say you have a matrix that looks like this. You have 2s on the diagonals, and then above that you have, say, 3, 4, 5. So A minus 2 times the identity would be this strictly upper triangular matrix. If you were to square that, you would have this even more strictly upper triangular matrix. And if you were to take the cube power, you would get 0. Okay, so the kernel of A minus 2 times the identity cubed is all of C3. The kernel of A minus 2 times the identity squared is the span of E1, E2, and the kernel of A minus 2 times the identity is equal to the span of E1. So let's construct a basis. Of C3, starting with a vector in kernel of A minus 2 times the identity cubed, but not in kernel of A minus 2 times the identity squared. For example, an obvious choice is to start with V, I'm going to call it V3 equal to E3. Then set V2 to be A minus 2 times the identity applied to V3, right? So this will be 4, 5, 0. And let's set V1 to be A minus 2 times the identity squared applied to V3, right? So in this case, we would get 15, 0, 0. Right. So notice, so I picked a vector that was in the kernel of A minus 2I cubed that's not in the kernel of A minus 2I squared. So I'm guaranteed that V2 and V1, even before I compute them, will not be 0. So we get a basis. So this would be V1, V2, V3, right? So 15, 0, 0, 4, 5, 0, and 0, 0, 1. This is a basis of C3. And in this basis, right? So let's work out what A looks like in this basis. So the first column would be A of V1 expressed in this basis. The second column would be A of V2 expressed in this basis. And the third column would be A of V3 expressed in this basis. Now this turns out to be really easy to compute because A of V1 I can write as A minus 2 times I V1 plus 2 times V1, right? And that's equal to 2 times V1. AV2 is equal to A minus 2 times the identity V2 plus 2 times V2, right? Which is equal to V1 plus 2 times V2. And A times V3 is A minus 2 times the identity V3 plus 2 times V2. And that's equal to V2 plus 2 times V3. So the matrix that we get is exactly the Jordan block corresponding to 2, 3. And this works in general. So if A minus lambda times the identity to the K applied to the vector V is 0, and A minus lambda times the identity to the K minus 1 applied to the vector V is not equal to 0, then the set, this is known as a Jordan chain, V and then A minus lambda times V, and then corresponding powers up to A minus lambda times the identity to the K minus 1 of V. This is linearly independent. Okay, so how do we prove that? Well, like all proofs of linear independence, assume that you have a linear combination of these equal to 0, and let's show that all of the coefficients have to be 0. So applying A minus lambda I raised to the K minus 1 to both sides, we get that A1 times A minus lambda times the identity raised to the K minus 1 applied to V is equal to 0. Hence, A1 is equal to 0. And then an easy induction, which I'll let you finish. Once you know that A1 is equal to 0, you can show that A2 is equal to 0, and inductively you can show that all of the coefficients are equal to 0. So the conclusion is that each AJ, each of these blocks, is in an appropriate basis, right? A basis made up of Jordan chains, a matrix of the form so you'd have some Jordan block corresponding to lambda j, say of size k1, then some Jordan block corresponding to lambda j of size k2, and so on until you have some Jordan block corresponding to lambda j of size k, say capital M. And zeros everywhere else. Right, so each block matrix AJ is in turn block diagonal, but now on the diagonal you have Jordan blocks. And here, these Ks, of course, add up to the algebraic multiplicity of lambda j. So any n by n matrix with distinct eigenvalues lambda 1 through lambda k is similar to a matrix of the form just like this, but now you'd have some Jordan block corresponding to lambda 1, some possibly another Jordan block corresponding also to lambda 1 perhaps, and so on until you'd end up with Jordan blocks corresponding to the kth eigenvalue. And this is block diagonal, everything else is 0. Right. Notice that you might be repeating, right? So you might have a, you might have 2, 2, 2, 1, 1 as one of your Jordan blocks, then 2, 1, 2, and then 2. So you might have a matrix like that. So this is the generalization of diagonalizability. Every matrix with complex entries, square matrix with complex entries, is similar to a block diagonal matrix where the blocks on the diagonal are Jordan blocks. And this turns out to completely determine the matrix up to similarity. So just knowing the Jordan blocks that you have tells you whether or not two matrices are similar. So this is the what takes the place of diagonalizability for an arbitrary matrix. Okay, we'll stop there and pick it up next time.